Okay, welcome to Lab 5, which I chose to be about the motion of a falling slinky. So, the motion of a falling slinky provides a fascinating demonstration of physics principles in action. As it descends, the slinky coils compress and stretch in response to gravitational forces, resulting in a distinctive undulating motion that highlights the interplay between gravity and elasticity. The purpose of this lab was to analyze the motion of a slinky and use a computational model to determine if the bottom of the slinky would stay stationary as the slinky was dropped. And then the results show that due to a net force of zero acting on the bottom of the slinky at the start, the bottom does not move unless it is acted by an outside force. So, some fundamental principles and concepts covered in this lab. So, obviously, we have Newton's second law, which is the momentum principle, and with that comes the velocity update and the position update formula. The force of gravity, which acts in the negative y hat direction, and g equals 9.8 meters per second square. And then the drag force, which is negative b v squared v hat, where b is some drag coefficient that we will define. So this diagram here represents the slinky before it is dropped. So as you can see, the only forces acting on it are the force of tension and the force of gravity, and they cancel each other out. So the bottom of the slinky is in equilibrium and does not move. And after the drop, um, the forces acting on it are the force of gravity and the drag force pointing upwards or in some other direction. Um, so as you can see, the forces change before and after the slinky is dropped. So I analyzed the motion of the slinky in this video. It just provides an example of a slinky being dropped, and I inserted the video into Tracker to be able to extract data from it. So the initial conditions I made in my computational model. So obviously we have the slinky's mass, which was 0.173 kilograms. The initial position of the slinky, which was extracted from the video, and the initial velocity was zero because the slinky started from rest, and then the each time set was 0.033 seconds according to the tracker data. And then I set my proportionality to be 32.65. So before the drop, which was before 5.055 seconds, um, forces acting on the bottom of the slinky were the force of gravity and the force of tension. And then here I update my velocity and my position of the slinky accordingly. And then after the drop, which is before 7.888 seconds, um, after the slinky catches up to the bottom, I sum up these forces, which were the drag force and um, the force of gravity. Uh, and then again, apply the momentum principle to update the velocity and the position. So as you can see, these are the results. So this is the observed data extracted from the tracker, and then this is the predicted data from the computational model. So as you can see, they're very, very similar. So the computational model is able to very accurately predict the motion and behavior of the bottom of the slinky before and after it's dropped. So both the observed data and the computational model show that the bottom of the slinky remains stationary until the top of the slinky catches up to it. So, right about this point, the bottom of the slinky is stationary. The position is not changing until this point when the rest of the slinky catches up to it and it starts to move. So some possible sources of error that could have come up, tracking the point mass, so it could not have always been centered. The computational model could have some errors. The real world has other like forces at play that we weren't accounted for by this model. And then the drag force could also act in directions that aren't strictly in the y direction, which would affect the calculated velocity and position. So what does this mean in a larger sense? So before the slinky is dropped, the forces acting on the suspended slinky are in equilibrium, so they cancel each other out, and the net force is zero. And when the slinky is released, the coils collapse downwards from the top in a compression wave, and the bottom of the slinky remains motionless until the coils have fully collapsed and the compression wave reaches it. So I think analyzing this motion before and after it is dropped can reveal a lot about the elasticity and the compression waves and forces at play within a slinky that can influence its motion and cause it to change its velocity. Thank you.